Strengthening of existing buildings. The topic is related to the use of advanced material to have a non-invasive solution to increase the seismic performance of existing buildings. So just a few words about the outline of our talk, a little introduction related to the main deficiencies of existing buildings in the European area against seismic action. Then we will talk a little bit about the seismic risk mitigation policies with a particular care to what we are doing in Italy. And then we will focus on the use of advanced materials for seismic strengthening. And we will discuss several experimental programs carried out at the University of Naples here in Italy on full-scale members. In particular, we will look at the use of advanced material to increase the performance of masonry and reinforced concrete buildings, and we will focus on the behavior, out-of-plane behavior of T-shaped walls in the experimental program 1, and then we will look at the behavior of beam column joints strengthened with advanced materials in the experimental program named 2 and 3, and then we will move into the conclusion and future needs. So, as well known, there are several countries in Europe prone to earthquake, especially in the south part of Europe, as clearly, as it can be clearly seen by the European seismic hazard map. And if we just look at what happened last year in 2020, we can see two devastating earthquakes in Croatia or in Aegean Sea with a lot of collapsed building and casualties. If we look to what happens in Italy, what happened in Italy over the last 50 years, we had about 5,000 casualties and about 3 billion per year for management of the emergency phases and for the reconstruction process. So that's why it was clear that something should be done to reduce the seismic risk. And starting from 2017, in Italy, we have approved a ministry decree involving the guidelines, the seismic risk classification construction. So Italian guidelines were issued in order to have a classification of construction exactly in the same way of what we do for energy efficiency, starting from A+ for very high performance buildings against seismic action, and up to G class, which is the worst class in terms of seismic behavior of existing buildings. To compute the seismic risk class, it is necessary to evaluate the seismic safety of the building and also the expected annual losses. By using these two parameters, it is possible to obtain the seismic class. And according to Italian decree, it is possible to explore tax deduction in the range from 70% up to 85% in case of seismic strengthening. So if you enhance the seismic risk class with strengthening intervention, you can explore tax deduction. And starting from 2020, this value has been enhanced up to 110%. So this is the reason why it is clear that it is really important to find solution to increase seismic performance of existing buildings, and we can do it when the building is partially or completely occupied. So we need to use strengthened solution that can be applied mainly from the exterior of the building, and that's why we are looking at the use of advanced materials and solution and techniques. And what we will focus today is the use of composite materials, starting from FRP textiles or bars, and then we will discuss a little bit also about FRC. In the world of composite system, there is also FRCM, but we have no time to discuss today about this other solution. And this is the main layout of the talk of today. We will discuss about the deficiencies of existing buildings, starting from masonry and reinforced concrete buildings, and then we will investigate the effectiveness of strengthening solution based on the use of innovative materials by laboratory full-scale tests. And finally, we will later discuss about the possible modeling and code standard specification evaluation. So, starting from masonry structures, it is really well known that the capacity of masonry buildings is mainly limited due to overtuning of masonry walls, which could be simple in the worst case, a composite, like in this case, but is a premature failure mechanism due to the poor connection between orthogonal walls. So the idea of the first experimental program that we will discuss today is to validate the effectiveness of a solution which is an alternative to the injected anchors based on the use of steel anchors. And in this case, the idea is to use CFRP, so carbon pultruded bars, tubes, wrapped with longitudinal and spiral stainless steel fabrics as injected anchor solution to increase the out-of-plane capacity of masonry. To do that, we realized a specimen, a T-shaped masonry specimen made by yellow tuff blocks. And to simulate existing buildings, we realized a very poor connection, just 10 centimeters with a discontinuous connection between this wall and this wall, the spine and the front wall. And then we apply in the lab the gravity loads, two different gravity loads, as happens in the real building, and then horizontal action to exactly simulate the effect of the earthquake on the building. And this is the first response of the specimen. We did a quasi-static monotonic test by applying an horizontal load in this direction. And so we are plotting here the horizontal force against the drift, which is the horizontal displacement over the height of the wall. So the black line is the experimental behavior, and as you can see, it is in between the theoretical force prediction related to mechanism 1, which is the simple overtuning, and the mechanism 2, which is the composite overtuning. So the specimen behaved exactly as we can find in real buildings. Then we repaired it and we did a cyclic test in order to evaluate the effect of cyclic action as actually happens in case of a seismic event. And you can see the blue curve is the envelope of the cyclic test. And here you can see the crack pattern with a clear, very clear mechanism 2, which is the composite overtuning mechanism. So in order to increase the performance and to avoid the overtuning, what we used was injected anchors based on the use of hollow pultruded carbon fiber tubes, here the mechanical properties, and then to improve the bond between the anchors and the surrounding masonry, we used the stainless steel fabrics wrapped around the bar. So here you can see the layout of the strengthening solution and the bars inserted in the wall in order to connect this wall to this one. And this is the laboratory phases. And also important is that the injection was done by using a superfly cement-free binder, so based on lime and decopolisone. And this is good for historical building applications. So here you can see the comparison. This is what happened before the strengthening solution, and this is the behavior after the strengthening solution. So the grid line is that related to the strengthened specimen, and as you can see, the capacity was increased a lot, and then due to the anchors, we achieved a rocking mechanism without damage, and so without the overtuning of the wall. So the as-built had an overtuning with a clear crack here. In this case, we achieved the rocking of the specimen just by using this kind of solution. And if we compare the behavior of the as-built and reinforced specimen, we could underline a very strong increase of out-of-plane capacity, plus 175%, and also in terms of ultimate drift and energy dissipation capacity, the increase were about 80 and 250%. So this technique was demonstrated to be a sound alternative to traditional steel-based connection, which could have some problems related to corrosion, and also it is a non-invasive technique, and the use of cement-free mortar could be suitable also in case of historical buildings. Then we move throughout the analysis on how design this strengthening solution. So we did some pull-out tests on glass, steel, and carbon fibers, just to evaluate the maximum pull-out force and to correctly design the strengthening solution that we have discussed in previous slides. And we collected our test results with other available results in the literature, and by using a multivariate regression analysis, we were able to derive a theoretical formulation to predict the maximum pull-out force. And this is the comparison between the theoretical prediction and experimental values. Then, once we achieve this value and a good agreement between theoretical and experimental values, we move it throughout the design by testing procedure to a 5th percentile prediction force, which is given by this expression. So exactly in the same way, we did something to look about the performance of RC structures. In this case, it is known that the main deficiency is related to the poor capacity of beam column joints, so the panel connecting the beam, the horizontal structural element with the column, the vertical structural element. And the reason of this deficiency is the lacking of stirrups, which is typical of European Mediterranean area buildings, and also the poor details. So what happens in earthquake is always that we can see cracks like this in the joints. So the idea was to carry out some experimental tests to validate the effectiveness of advanced materials solution for low impact interventions based on the FRP solution. And we focus on exterior joints, which are the unconfined ones, so the most vulnerable ones. This is the joint, and this is the laboratory view of the specimen. This is how the joint is behaves during an earthquake, and this is the equivalent solution that we have in our test setup solution. Here you can see that we applied the axial load to have a constant axial load, as happens in the real application, so the gravity load, plus the cyclic action given by this actuator, which is the solution to reproduce what happens in the joint panel during an earthquake. So this is the specimen details with no stirrups inside the joint, as commonly happens in existing buildings. And this is the load history applied by the actuator in terms of drift, which is the displacement or the beam length. So what we did was 6 tests, 3 on control specimens, so without strengthening solution, and 3 on specimen strengthened by using the FRP. 2 classes of concrete, very, very poor, about 13 megapascal, and poor concrete, about 16 megapascal, and this is commonly found in existing buildings. And then we investigated on the use of 2 possible scheme solutions. The light one with the quadriaxial carbon fibers applied just on the joint panel with only the connection made by U-wraps. And then a second solution, which is a little bit less invasive, but by also wrapping the columns, and this is done to increase the ductility of columns once the joint shear failure is prevented. Scheme 2A and 2B differs because in the case 2A we have 1 layer of reinforcement on the joint panel, while in case of 2B we have 2 layers. So I will show briefly the experimental outcomes. This is the control specimen, which failed due to shear cracks in the joint panel. This is the the behavior of the specimens strengthened with FRP in light solution, light scheme, and we are comparing the results in terms of shear recorded in the column versus drift. And here you can see the envelope of these two behaviors for control and strengthened specimen. As you can see, the strengthening solution allowed to increase the strength capacity by a factor of 18%, but no ultimate drift increase was achieved due to premature debonding of FRP. And this is because we just used one layer and the anchors was not able to prevent the debonding. But in any case, we achieved a good energy dissipation, which was 16%. In case of strong scheme, so by adopting the more invasive solution, again, the comparison between control specimen and strengthened one, and here you can see the envelope curves for the control specimen and strengthened ones. In this case, we achieved a more significant strength increase, up to 28 and 46%. And in this case, we obtained the maximum performance because we also avoid the joint shear failure, which was achieved here because we used just one layer. But by using two layers, we avoid the joint panel shear failure and we attained the plastic hinge. And this was the reason why we attained also the maximum ductility and the maximum energy dissipation capacity, which was about 30%. So, exactly as before, then we moved on the possibility to design this strengthening solution and to compute the real contribution of FRP. So we proposed a strength capacity model which considers the FRP contribution to the principal tensile stress. So the idea is to compute how much FRP can contribute to the maximum joint shear stress, which depends on the joint panel principal tensile stress. And this value can be considered as the sum of concrete contribution, which is the first cracking, given by the very known formulation provided by Priestley. Then, since no stirrups is inside, we use FRP to contribute to close these cracks, to sustain this action. And the idea is to compute the FRP contribution as the product between the area of FRP in this direction, so the equivalent FRP area, times the stress in the FRP, which is given by the Young modulus times the strain. And the very important thing is to calibrate how much is the effective FRP strain. To do that, we collected data on several tests along with our tests, on beam column joints, strengthened by using FRP, and when FRP failed. And what we did was to find a correlation between the strain, the effective strain, and a parameter which is given by the area of fibers, the equivalent area, the Young modulus of fibers, and the concrete compressive strength. And this is the proposed formulation, which has a good match with the experimental results. And it also takes into account the initial damage of the joint or the use of mechanical anchorages. Then, to give to practitioners a formulation, we move from here to here, and this is the value that can be used in design applications, so the 50th percentile. And this expression was also inserted in the last FIB bulletin related to the use of externally applied FRP reinforcement for concrete structures. So in the chapter 8, which is related to the seismic retrofitting, you can find the approach that we have discussed before and the formulation which was calibrated based on this study. And now we have a lot of applications based on the use of FRP in Italy and in the area where earthquake happens in these years, as shown by this picture. And we also provided a book to give some suggestions to practitioners to how they can realize and design the strengthening of structural elements. Finally, experimental program 3, there are some cases on which FRP could be not the best solution, especially when the concrete is very poor, damaged or deteriorated, because in this case it is necessary to apply FRP on a better substrate. And so the idea is why we do not use in these cases a fiber reinforced cement composites. So why we do not use a thin jacketing by using a fiber reinforced mortar cement composites in order to remove the concrete cover and apply this layer without any other reinforcement. So the occasion, the opportunity to evaluate the effectiveness of this solution was given when a building damaged by L'Aquila earthquake was found no more reparable. So according to practitioner studies, it was decided that it was not viable due to costs to repair the building and to strengthen it. So the idea was to demolish it because in some parts the concrete was very poor. And so what we did was to extract during the demolition phases, some beam column joints, real beam column joints. We moved it in our lab, and here the details of the specimen, and we tested it in the as-built configuration, and as expected, the shear failure was achieved in the panel. And then what we did was to remove the concrete cover and use as a retrofit technique FRC system, FRC jacket. So a thin jacketing made by FRC with the steel fibers in a volume ratio lower than 2%. Here you can see the steel fibers and the compressive behavior of this system and the tensile behavior, which is characterized by a residual capacity due to fibers bridging, which is very important for this kind of application. So the question was, can the FRC jacket be a sound alternative to FRP? And so we removed the concrete cover on the second specimen. We applied this new concrete cover, which works also as a repair and strengthening solution. And then after the test, this part was completely undamaged. The cracks developed on the beam. And if we compare the performance of the control specimen with that one with the strengthened one, and here you can see the envelopes, you can clearly understand that there was a good strength increase in the range of 37 up to 54% if we look at positive or negative performance. And then the increase in terms of energy dissipation capacity was about 85%. Obviously, this is a new solution. Proper design formulation are needed, but it's a good opportunity, especially when concrete is very poor. Now, an ongoing research that we are performing now in a new lab with a reaction wall is a pseudodynamic test on a 2D RC frame, which reproduce a real building frame which was damaged by L'Aquila earthquake. So we realized exactly the same frame, and we are performing pseudodynamic tests, and the idea is to also evaluate the interaction effects within fields and then to investigate on the possible solution based again on FRP plus anchors wholly applied from the exterior side, again to have a very limited impact and disruption for occupants. So just to conclude, advanced materials based solution have been demonstrated to be really effective to increase the seismic capacity of existing buildings. And innovative systems require advanced design tools. This implies a continuous updating of the scientific and technical community. And also the use of sophisticated software are needed in order to have a refined modeling. And only in this way we can apply advanced technologies, and they can be introduced in a very traditional market as the construction market. And this could be also very important for the economy, especially now after the pandemic and the COVID that we have. So as future perspective, the use of advanced materials should be validated by experimental programs, possibly on full-scale specimens, and it is really important in case of seismic application to investigate the use of solution applied wholly from the exterior of the building, and also to derive reliable design formulation so that practitioners could use these materials in a safe way. And this is a list of references if you want to go into the details of what we discussed today. And this was the last slide, and really thank you for your kind attention.